Yeah? The irreversible path is very sudden, and we'll discuss some of the irreversible versus reversible changes. Reversible changes usually are slow. Okay, so it will come to some of the paths which are very special, and you'll definitely get to hear a lot about them, is something called isothermal. So iso essentially means same, and thermal is for temperature. Then you have isobaric, which would stand for pressure, or adiabatic or adiabatic. So as to break it down, would be no heat exchange. Yeah, no Q. So I'll just define heat by Q exchange. Okay. And we'll discuss a bit more about these kind of systems for particular things. So let's then come to the zeroth law. Now, let's say we've connected two bodies, and one body is A, which I say is hot, the other body is B, which is cold, and then I connect these two together. Yeah, let's connect them, bring them close, and of course finally they'll become warm. Yeah. A, B, both of them will attain some kind of an equilibrium. Well, yeah, most of the things that we are discussing is equilibrium thermodynamics. So heat flows from here, A to B, and then it becomes warm. Everything is at the same temperature, which means that such a system allows us to define the temperature. For example, yeah, since these are both at the same temperature, if B is a property that B has a property that could be measured, B could be a thermometer, right? And you have various different kinds of thermometer. In fact, what you need for a thermometer is, one thing, you need a material, for example mercury. Another thing, you need a property. Yeah? For example, in the conventional mercury thermometer, the property is that the volume changes as you increase the temperature. Right? The other thing could be the electric current changes as you change the temperature. Yeah? The conductivity of metals goes down as you increase the temperature. So you could have any of the property which is measurable. So let's just call that property F of temperature T. Then you need some reference points. Well, it could be melting point, it could be boiling point, and 2 would be enough if you have an interpolation scheme that's linear, right? So if f of t is a function like m of t plus c, then it's a linear interpolation scheme. Then I don't need any more points. If it's not linear, then I need a lot more points to establish what kind of an interpolation scheme is required, right? Now, and there are lots and lots of scales. I've written some of those in the handouts. You could go through them. There are very interesting stories behind them. But let's just see what the ideal gas, and that's more important for thermodynamics, right? What the ideal gas thermometer would be like. What's the property? Now, for the ideal gas, what I know, yeah, we know the Boyle's law, right? The Boyle's law is P times V is a constant, or let's call it V bar, which is molar volume. Yeah, I'll put a bar for molar volume, and I want to see, well, of course the Boyle's law is valid when you have very small pressures of very high volumes. So it's essentially valid at very dilute gases. So I have a very small pressure, so limit of P approaching 0. This is my function, and this function changes as the temperature changes. Well, all I could do was to plot this f of as a function of temperature, right? And I already have my Celsius scale or the centigrade scale. So this is my 0 degrees C, and this is let's say somewhere 100 degrees C, the melting and boiling points of water. And let's plot this. Oh, very linear, very linear. Yeah, let's say that point and this point. Now then I say, okay, at some point of time this f of t also goes to 0. Extrapolate, sorry. And the moment you extrapolate, you get a temperature over here, okay, which is minus 273.15 Kelvin to be very precise. Yeah. Oh, not Kelvin. So I'm precise rather. Degrees C. Yeah, degrees C. So let me define absolute 0. So 0, and let's define the scale as Kelvin. I don't write the degree before Kelvin. Okay, is equal to minus 273.15 degrees C. Good. So change the 0 to 0 Kelvin now, and that's your absolute temperature scale. Yeah, so that's your absolute 0. Good. So far so good. Yeah. So now this is linear. Yeah, it's a very linear temperature. Now I've changed the 0, so now my function is no longer a function of small t, it's a function of capital T, and the capital T is essentially temperature in kelvins. Okay, so from here I know at 0 Kelvin, and what else? I need another reference point. I could have taken the melting point, I could have taken the boiling point, but which we'll come to later. The triple point where both, oh, sorry, not both, but where all the three of these, so water in gaseous, liquid and solid state coexist, would be called the triple point of water. All the three, right? Temperature at triple point. And since we know it's linear, let's just extrapolate it. Let's just join these 2 points, and the temperature what you get over there is 273.16 Kelvin, not 15 Kelvin. 15 was the melting point. 16 Kelvin, very precise, is the triple point of water. But it's not at 1 bar. Yeah, the melting point is defined at 1 bar. So this also needs a definition of at what pressure are we going to do this, right? So that's your temperature axis, that's your function PV, and the pressure at which the triple point exists is 6.1 into 10 to the power minus 3 bar. So very small pressure compared to an atmosphere. Yeah, millibar, 1000 times less. Okay, we'll come to these things a bit later. We'll definitely come to the triple point and see why you need to define both temperature and pressure. Otherwise, it's not really the triple point. Otherwise, you would have many more points. Okay, we'll come to this maybe in the 6th lecture. Let's see. Well, now to define the gases, yeah, what you had was the function of temperature, right? Function of temperature, which is quite linear. So with temperature, so I could write that as R times, which is some constant, times the temperature.